An isolated 3 kilogram object initially at rest explodes and splits into 3 fragments. One fragment has a mass of 0.5 kilogram and flies off along the negative x-axis at a speed of 2.8 meters per second. And another has a mass of 1.3 kilogram and flies off along the negative y-axis at a speed of 1.5 meters per second. What is the speed and direction of the third fragment? Well, this is the same as you keep a nut on a table and hit it with a hammer. What happens? The nut will break and the pieces will fly off in all directions. Why do the pieces fly off in all directions? Well, to conserve momentum. The law of conservation of momentum. What is the momentum of the nut before you crack it? 0. That means after you crack it, if you add the momentum of all the pieces, it must be equal to 0. That means if one piece flies off in the positive direction, another piece flies off in the negative direction, the total momentum there will be 0. Well, this is the situation here. We have an object that explodes. And I have actually put those 3 pieces there. It explodes into 3 pieces. What is the total momentum of the object before exploding? 0. That means the total momentum of the 3 pieces, when you add, must be equal to 0. That is the principle we are going to use in solving this problem. Okay. Total momentum of the object before explosion, Pi equal to 0. Well, it's going to explode now. Watch what happens to the first piece. One fragment that has a mass 0.5 kilogram moves to the right. So it goes to the right with a speed of negative 2.8 meters per second I. Why negative? In the negative x direction. And we know its mass. Its mass is 0.5 kilogram. The second piece goes in the negative x direction with a speed of 1.5 meter per second. So the velocity of the second piece is negative 1.5 meter per second j. Now watch how we represent the x and y directions. It's very important to do that. And now what happens to the third piece? The third piece must go somewhere in that direction so that the total momentum remains 0. We need to find the final velocity of the third piece, and I call it V3F. So V1F is negative 2.8 meter per second I. V2F is negative 1.5 meter per second J. We need to find V3F. Alright, let's set it up. Mass of the first fragment is 0.5 kilogram. Its velocity after the explosion is negative 2.8 meter per second I. Therefore, what is its momentum after the explosion? Let's call it P1F. Final momentum of the first object. Its mass multiplied by its velocity. What's the direction? It's very important. That will be negative 1.4 kilogram meter per second I. This is the momentum of the first fragment after explosion. Let's now take the second fragment. The mass of the second fragment is 1.3 kilogram. Its velocity after explosion is negative 1.5 meter per second J. Therefore, P2F, the final momentum of the second object, its mass times its velocity and that is negative 1.95 kilogram meter per second J. What is the mass of the third fragment? The total mass before explosion is 3 kilogram. Out of that, the mass of the first kilogram is the mass of the first fragment is 0.5 kilogram. The mass of the second fragment is 1.3 kilogram. Therefore, the mass of the remaining must be 3 minus the sum of the masses of the first two pieces. That will be 1.2 kilogram. So, the mass of the third fragment is 1.2 kilogram and its velocity is v3f. Let's go to the other slide. And I have brought all these important values with me. Final momentum of the first fragment, final momentum of the second fragment, and the mass of the third piece. Well, what is wrong in here? The mass is not a vector quantity, so just take away that J. That J does not belong there. Okay, let the velocity of the third fragment v3f, remember v3f is the velocity that makes an angle with the x-axis. So let's say its x component is x and its y component is y. So let v3f be xi plus yj. I hope you understood what this is about. If you remember, this is the v3f that we have drawn. Its x component, we are simply going to call it x. And the y component, we are going to call it y. We need to find these x and y. So let the velocity of the third fragment in the component form be v3f equal to xi plus yj. Then its momentum will be p3f equal to 1.2 kilogram mass times velocity. Velocity is xi plus yj. Now, what is therefore the total momentum of the three fragments after explosion? It will be P1F plus P2F plus P3F. This is P1F, negative 1.4. This is P2F, negative 1.95. Plus, this is P3F, mass of the third fragment, times its velocity in the component form. That means the momentum of that third piece has an x component and a y component. What is the x component of this momentum? It will be 12xi. And the x component, the y component of this momentum is 12yj. Alright. So, Pf, let's combine the i's and the j's. Look at this. The final momentum can now be written as the final momentum of the third fragment in the x direction is 12xi. And the final momentum of the first object is negative 1.4i. We can add the momenta in the x direction. It will be 1.2x minus 1.4i. That is the x momentum of the three fragments after explosion. And what is the y momentum of the three fragments after explosion? The y momentum of the third fragment is 1.2yj, and the momentum of the second object is negative 1.95j. Add those two together, that will give me the y momentum of the three fragments after explosion. That would be 1.2y minus 1.95j. This is the most important step here. The final momentum in the component form. We added the x components of all this and then the y components to obtain this. Well, using the conservation of momentum, you know that Pf equal to Pi, and Pi, the initial momentum, is 0. Therefore, the final momentum also must be 0. Well, if the final momentum is 0, it means the x component of the final momentum is 0, and the y component of the final momentum is 0. Is that right? They separately has to be 0 if the final momentum is 0. So we first take the x component and set it equal to 0. 1.2x minus 1.4 equal to 0. Solving that for x gives me x equal to 1.17 meter per second. What does x represent? X represents the x component of the velocity of the third fragment. We are looking for V3F, this V3F. And this 1.17 is the x component of that velocity. Similarly, take the y component of the final momentum and set it equal to 0. And that gives me y equal to 1.63 meter per second. So what is V3F now in the component form? V3F is xi plus yj. We have solved for x and y. It's equal to 1.17 meter per second I, that is the x value, plus 1.63 meter per second j. And we can now find the magnitude and angle of that velocity. You know how to do that. The magnitude of V3F is square root of x squared plus y squared. And that is 20 meter per second. And what is the angle? How do you find the angle? Theta equal to tan inverse of y divided by x. Theta is tan inverse of y is 1.63, x is 1.17. And that is 54 degrees. That means after the explosion, the third piece will move with a velocity of 20 meter per second at an angle 54 degrees, so that the total momentum of the three pieces after collision is 0. Isn't this a beautiful problem? I think so. Well, I want you to go through this and learn the technique of this problem one more time. Okay? Let's look at another problem.